you look at two adjoining links. So here I've shown two links. I've attached a frame at the pin joint, which is always done, right? Okay, so you can see that OI minus 1 is with respect to O minus 2, which is the previous one, and this one is this is the position with respect to the previous frame, which is this is frame I minus 1, and this is frame I, right? So this is, yeah, this I, yeah. So this is giving the position of I with respect to this frame, and that's always the case, and so on. So we could have two cases of Q dot. If it is theta dot, it means the revolute joint. And we've not really looked at prismatic joint in this course, but you could also have a prismatic joint. A prismatic joint allows you to move linearly. It doesn't lead to rotation. These are taken from a book called by Craig, and you can refer to it if you want. J.J. Craig, chapter 5, page 146. So the way this is computed is we compute the angular velocity of frame I with respect to frame I minus 1. Okay, how is it done? Well, the angular velocity of frame I with I minus 1 would involve the rotation matrix because we're relating two frames, but then there's also a part due to the fact that there's a revolute joint or a prismatic joint. In this case, we're looking at revolute joint. So revolute joint at frame I. Okay, so this basically follows from reasoning about the angular velocity. So this is the angular velocity of this frame. So this frame. That's how the frame would rotate with respect to its previous frame. This is the linear velocity, or it's the velocity of this frame I with respect to itself. You need the rotation matrix, you need the velocity of the previous frame, so this will be V I minus 1, I minus 1. This will be VI, VI. Angular velocity of the previous frame OI, I minus 1. So this is the position of this with respect to that frame. So everything here you see is how one frame is related to the previous frame. Now, if you have a prismatic joint, it kind of simplifies because the main simplification is that you see that there is a contribution due to the pin joint. There's going to be nothing here because that pin joint, this is basically a sliding joint, so it's not going to contribute towards the rotation part, but it will contribute towards the linear part. So there's a contribution to the linear velocity. So that's how you get the linear and angular velocity of the frame. Okay. We're also interested in finding the linear velocity of the center of mass, which I've shown with the red dot. Right. That can be found by knowing the velocity of the frame plus omega cross PCI. PCI being the distance from the frame, body frame, to the center of mass. Okay. So everything here is, as I said, relative of one frame with respect to the previous frame. That will simplify our life a little bit later. So let's go to the next part. Now, how to use the formula? Well, this is a recursive formula, right? It goes from frame, well, I minus 1 to I. So what you do is you start with frame 0. Frame 0 is the frame which is attached to the world. It does not move. So it's the linear velocity and the angular velocity of frame 0 is going to be 0. So once you know the linear angular velocity of the 0th frame, 0, 1, 2, and so on, we can then compute the velocity of this with respect to this, right? Because this formula gives you how I, well, let's say put I equals 1 is related to I minus 1. So I minus 1, 1 minus 1, 0. So you know the velocity is 0. So you can find the velocity of frame 1, and same for the linear velocity. So that's what you would do in a recursive fashion. So you'll go from here to here and so on. So once you do this calculation, all you'll get is the velocity of angular velocity of the body frame with respect to itself, omega I with respect to I, right? I with respect to I. Sometimes you want the velocity of the frame I with respect to the world frame, which is the zeroth frame. That is, how is it moving with respect to the world? All you do is take the velocity with itself and multiply with the right rotation matrix, and you have the velocity. It's super easy. Same for the angular velocity. Okay, so Ri0 will come from the homogeneous matrix. There's one more thing which you're interested in. You're also interested in figuring out what is the velocity of the end effector, right? So the end effector is E. If you want the velocity of the end effector, you take the velocity of the nth frame, which is probably attached to the nth degree of freedom. And then you just use this formula, which tells you the angular velocity of the nth frame, linear velocity of the nth frame, times the position of the frame E of this point with respect to this frame. So it's just this vector P E in with respect to frame N. The good news is that omega E is same as omega N. So you don't have to do much, but for the velocity, you need to do certain bit of work. And then the global velocity for this is simply same thing. You need to take the rotation matrix, which comes from the homogeneous matrix, into it. So the best way to illustrate this is to actually do a problem. So that's what we'll do next. Yeah, I'll take the planar manipulator. We'll do this by hand. I'll write down the formulas. Then we'll go to MuJoCo and see what we get from the formula. And MuJoCo also provides a method where you can check your calculations against its own. It keeps track of all these things itself. So I'll show you how to do that too. That you can actually get the velocity of the body frames. This is something we've not done before. Okay, so let's apply this to the planar manipulator. This is the frame 0 is always fixed 0, and then frame 1 would be the one which is along this, and then frame 2, and then frame 3. Right? So frame 0 is fixed, it's not moving. Frame 1 is the one which is attached to theta 1, frame 2 for theta 2, frame 3 for theta 3. Okay, and the question here is we need to compute what do you want? We want the velocity of frame 1 with respect to 0, velocity of 2 with respect to 0, velocity of 3 with respect to 0. So they're the linear velocities. Then we want the angular velocities. Yeah, and then I've not shown the center of mass, but let me quickly show that. So let's say that there's a COM. Let's call that C1, C2, C3, so on. So I want the velocity of C1 with respect to frame 0, C2 with respect to frame 0, C3 with respect to frame 0. And then there's an end effector here. So it's this one. So velocity of the end effector with respect to frame 0, and the angular velocity of the end effector. Lin angle of frames. This is the, oh, I forgot to add. Just add the, not needed. Of center of mass. Lin well, lin of end effector. Okay, now I did not put the angular velocity of the center of mass because the angular velocity of the center of mass is pretty much the angular velocity of the frame. So it's the same thing. You don't have to really compute that. Okay, so what I'm going to try to do now in the next, we only for 7 minutes, is to write down formulas for V1, V2, and so on. And then we'll take those formulas to Python, and then that'll give us a way in which we did the calculations ourselves, but then we'll verify that with MuJoCo. So here is how you would do this from, so I'll use these formulas for the revolute joint because we have only revolute joints. We don't have a prismatic joint. So I need to use these formulas. Okay, so first of all, omega 0, 0 is equal to V0, 0 equals 0, 0, 0. Right? That's the speed of the world frame, which is 0. Next, omega 1, 1 would be R10 transpose omega 0, 0 plus theta dot 1. Here n is just k, right? It's in the z direction. And then V11 is R10 transpose P00 plus omega 0, 0 crossed with position of frame 1 with respect to 0. Okay, so this can be done for 2. R2, 1 transpose omega 1, 1 plus P11 plus omega 1, 1 cross O21. Okay, so you get the idea. We need to also write the formula for omega 3, which I will skip, but it's fairly straightforward now that you see the pattern. So you can fill that up yourself. Okay, but these are only giving you angular velocity in its own frame. We need to relate this with angular velocity in the world frame, right? So for that, what you'll do is V1 in frame 0 would be R10 V11. And then V20 is R20 V22. And same for V30. Similarly, for omega 10 is R10 omega 11. And same for omega 30. I'll not write it down. So we have basically computed all these things which were asked. One of the things was asked was these. So these have been done. I'll just shade them. Okay, that's how we'll do it. Now let's move on to VC1, VC2, VC3. So that would be the other formula I wrote down. So the formula is right here. Copy. So velocity of C1 in frame 1 would be velocity 11 plus omega 11 cross PC, the position of this in frame 1. C2, 2 will be V22 plus R22 PC2, and I'll not write this down. 3, 3, you should write it down. It should be very straightforward. Okay, but this is giving you velocities in frame 1, 2, and 3. In order to find the velocity in frame 0, you finally have to do VC0, or VC10 is R10 VC11, VC2, frame 0 would be R20, VC22, and then VC3, you can write it down. Okay, so this is the second part. We had to compute VC1, VC0, VC3, which we did. This was the here. So this has been computed. Okay, and the last one is V0, VE and V omega E in frame 0. So for that, what we'll do is we'll use this formula. Here n is equal to, well, n is 3, right? The last frame. So let's take this. I'm almost done. P. Okay, so VE would be frame 3. And omega E3 would be omega 3, 3. And then to compute V in frame 0, you take R3 frame 0, because third is the last frame. Omega E frame 0 would be R30